is going to be about raising and lowering operators. We're going to talk about two special operators. The lowering operator, A operator, and the raising operator, A operator dagger. Let's give him another 20 seconds.
So,
Goed, ja, dus het gaat in en I can do a restart. Okay, so instead of starting the lecture, I start with a bit of motivation until everyone gets ready. We talk about harmonic oscillators. Why do we care so much about harmonic oscillators and quantum harmonic oscillators? One of the reasons is it's a solution to almost anything. Meaning, usually we have some function, potential, or whatever, and we can almost always approximate it around its minima. This is similar to what we did in the previous lecture when we had some potential that was something like 1 over x to the 12 minus 1 over x to the 6. It looks something like this, diverging. It was let's do it for x positive. So it was diverging and then coming slowly back to 0. And we said, okay, we can say this is not anywhere near to something which is harmonic or parabolic, but we can approximate it around its minima. So similarly, any function f of x, we can say that around its minima x naught, it's going to be f of x naught, some constant, and we don't care about constant in the potential energy. Then first derivative x minus x naught, then a second derivative x minus x naught squared. Because this function is around its minima, this goes to the garbage because f prime is 0. So this is one of the reasons we care so much about harmonic oscillators. It's because almost anything can be approximately an harmonic oscillator. Great. Now that everyone is ready, let's talk about harmonic oscillators, quantum harmonic oscillators, and about raising and lowering operators. So, we can look at the Hamiltonian of an harmonic oscillator and write it as P operator over 2m plus 1 over 2 m omega squared x operator squared. Nice. We're going to do a few adjustments to this equation to evaluate this Hamiltonian, this harmonic oscillator, non-Hamiltonian, that we know the solutions and everything. We're going to try and make it work as a function of A and A dagger operator. And then we're going to explain what they are more deeply. So, we can write this as Hamiltonian is equal to 1 over 2m m omega x operator minus IP operator m omega x operator plus IP operator. Great. You can open the parentheses and see you get the same result. We can keep So now, if you do it like this, we don't get exactly what we want. Why is it written like this? Okay, anyway. This is, what we are missing here is plus h bar omega over 2. Okay. Okay, so this is the way to write this Hamiltonian. We can write it like this. Because we get a term h bar omega over 2. This is because we don't care about it right now. We're gonna get into it later. Let's just assume this is the way to open it. Oh, because we are just two people, we can open it. Let's open it up. It's quite interesting. So we get omega over 2.
But in the Hamiltonian, you need to the p operator to be squared, right?
Yes. Let's open the parentheses to make it clear. So we have m omega x squared. That's what the x operator plus I m omega x operator p operator minus I m omega p operator x operator plus I minus plus p operator plus h bar omega over 2.
Wait, you need the
So what you want to
squared and omega squared on the first.
Yes, here you have squared omega squared. Yes, because when we divide it by 2m, we get the x operator squared. If we looked on this term, so the p squared over 2m, and it's p squared, right?
Yeah.
Yes, it's a mistake in the lecture notes. But here we have these two terms, which looks like they are identical, but they are not.
Commutation on it.
Yes, they're
IH bar maybe, I think.
exactly, because they are commutating. So what we're gonna get as a result is these two terms are gonna be equal to exactly minus h bar omega over 2. And this is why I added here an h bar omega over 2. Okay, this is clear, or we will do it's not clear.
H bar over 2 on the
Yeah.
Over h
Times m.
this h bar omega m, because we want to divide by 2m. Right, I meant with the coefficient, exactly. Okay. So we are happy. What I want to do, what I want to focus on is I want to change the Hamiltonian just to get out some variables to get dimensionless operators. Meaning, this is a little bit of a mathematical trick, so I'm gonna just say this is equal to, I'm gonna take h bar omega over m outside, so now I have h bar omega over 2. And then I'm gonna be left with m omega over h bar square root x operator minus I 1 over m omega h bar square root p operator m omega over h bar square root x operator plus m omega h bar p operator. You can have here plus 1. Okay, the 1 is for h bar omega over 2. And here I just took out h bar omega and multiply everything and inserted the m inside. And yes. So if you take the h bar omega, if you take a square root to here, 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 and here, it's gonna be the same. Why I did it? I did it because I want to define, I want these two parts. I want these parts have units of nothing, and this part will have units of nothing. Same goes for the other side. To have dimensionless operator. So I took the h bar omega, which has units of energy, same as the units of the Hamiltonian outside, and now everything inside is dimensionless. And how we do it? We do it with, because this term, this m omega over h bar, the square root, we're already familiar with this term. also square root of m omega h bar. We know that we defined last time sigma x and sigma p. Sigma x is h bar over m omega square root. Sigma p is similarly square root of m omega h bar. And we get that our Hamiltonian is equal to h bar omega over 2 x over sigma x minus I p over sigma p times x over sigma x plus I p over sigma p plus 1. So it's very similar because we know the eigenvalues for the harmonic oscillator look something like En is equal to h bar omega n plus 1. And we have here half. Yes.
Plus half.
Yes, exactly. Plus half. So it's getting a little bit similar because I can take the let's even move the h bar omega. Let's take here h bar omega. Here you have this is over square root of 2. This is over square root of 2, and this is half. So it's getting very similar to what we are familiar with. The reason is I can define something very unique. I can define a raising and lower operators. I can say this is a raising operator, a operator dagger, and this is a lowering operator. This is definition. I'm defining. And I'm gonna write it on the side in shortly, but I can say that the Hamiltonian can be written as h bar omega a dagger a plus half. Later we will call this a dagger a the number operator. It was a little bit fast. Let's do a short recap. What we did, we started with our regular Hamiltonian for the harmonic oscillator, for the quantum harmonic oscillator. We did a little bit algebra. We just played with the algebra, and then we defined two operators. Then we called it an operator for some reason, and later I'm gonna show you that this n operator gives you the quantum number. So this is a lot of big assumptions. It also looks like magic. There is some reason we define it this way, but it almost looks like magic. First, I want to focus on the lowering and the lowering. This is the A, and the raising, the A dagger. You can remember it by A. It doesn't have anything, so it lowers it, and the A dagger has like a plus, so it's like taking one up. So it's like a plus 1. This is also called, and I'm not sure we're going to talk about it in this quantum course, but it's going to be very important for future courses, as we're going to call it creation and annihilation operators. Just because you can look at it as one way to look at it as we increase the quantum level, decrease the quantum level, and then increase it, or destroy, annihilate something, and then create it again. But this is just some abstract stuff we're gonna learn in the future when we grow up. First of all, what is important to notice is this A and A dagger, it's not an emission operator. Meaning we know that if we have X operator and we take the dagger of it, what we get is X operator. Same for P operator. We take the dagger, we get P operator. This is because X and P are emission operators. They are stuff that we really measure when we do an experiment. A dagger is not equal to A. We can see it here very nicely because we can take the dagger here. We're going to get X dagger, which is the same as X. P is P dagger, the same as P, but here we have a minus and plus I. It's not equal. So if it's not equal, it means we cannot measure this operator in the lab. Meaning, I'm gonna emphasize that for X, we can have the average or predicted value of X operator. This has a physical meaning. But if we try to measure A operator, it doesn't have a physical meaning. A or A dagger. However, as we will see shortly, N does have a physical meaning. N is a mission. So if I take N, this is the number operator, it's equal to A dagger A. So let's look at N dagger. It's equal to A dagger A dagger, which is equal to A dagger, and here dagger, and here dagger. This is equal to A dagger A, which is equal to N. Meaning, there is some physical meaning for measuring N.
Just making sure the momentum operator is IH by dou over dou X, right?
Yes, but we can also write it as P. It's
Yeah,
the same as
so
we can
how
write
will
the location operator, X operator. We can write it in Fourier space as minus IH bar divided to the P. And P operator, this is space. This is Fourier space. P operator is going to be minus IH bar d to dx. Up until maybe there isn't a minus sign.
So if you take the dagger of P in the space representation, you'd have IH bar dou over dou X, right?
I'm gonna have IH bar, the dagger of dou to dx.
What does the dagger of dou over dou X mean?
You can check it. But it's like you learned math utilities 3, right? Math is 3.
I'm doing it now.
So what you learn is that a derivative in X space, derivative in X space is like a multiplication by K in Fourier space.
By IK, yeah.
IK. So it's a complex. So it doesn't mean
just make it in this. Okay.
So it's the same. It's still Hermitian. Doesn't matter. You're still gonna get the same Hermitian properties. But like to check what is the dagger of d over dx, it doesn't mean it's obvious it's d over dx. Maybe it's I times d over dx. Maybe it's minus. I don't know.
So we need to consider maybe Fourier space and stuff. Okay.
Sometimes Fourier space, sometimes real space or F space, whatever. Okay. Great. That's it. Okay, let's have a little bit of summary. Just try to make the board clean again. I'm gonna rewrite those two operators. So, the A operator, or the lowering operator is equal to X operator over square root of 2 sigma X plus I P operator over square root of 2 sigma P. A dagger, this is the raising, operator is equal to the conjugate. X operator over 2 square root of 2 sigma x minus I p operator over square root of 2 sigma p. While n operator is a dagger a operator. Great. So this is very nice and useful only when we have the following property. And this is, I think you did, or you're gonna do it in lecture, or maybe you don't and you should just know it because it's a little bit of a complicated derivation. However, we know that if we have we assume that phi n is the eigenstate of our Hamiltonian, of our harmonic oscillators, meaning n is the energy, the same n of En, the energy levels. We can write that A operator over phi n of x is equal to square root of n phi n minus 1 of x, and A operator dagger of phi n of x is equal to square root of n plus 1 phi n plus 1 of x. Note that A and A dagger are not an eigenfunction of the system. We cannot, they are not eigen, phi, the other way around. Phi n of x is not an eigenfunction of the operator A or of the operator A dagger, because you cannot get the same eigenfunction with an eigenstate. You get some eigenstate with a different eigenfunction. It is still very useful. Moreover, if we apply an operator to some eigenstate of the system phi n of x, we get A dagger A phi n of x, which is equal to A dagger, and which one is first? We need to make sure it's like a linear algebra that we don't switch between them. Because if we have A dagger A, which applies on some function, it's not equal to A dagger. This is similar to what we had in the start of the class, where we said that Px is not equal to xp. What it is equal exactly, we can see it from the commutator relations. Anyways, so here we have A dagger. We apply the lowering operator on phi n of x, so we get square root of n times phi n minus 1 of x. This is just a scalar, so we can take it outside and apply the A dagger operator, and then we get square root of n, we take outside. Here, square root of n minus 1 plus 1 phi n of x. Overall, we got that the number operators applied on some eigen function phi n of x gives us the number of the state times phi n of x. Meaning the number operator is in the same basis as the Hamiltonian. And hence we get that this eigenfunction phi n of x is an eigenfunction of this operator. Questions?
So what does the expectation value mean?
The expectation value of n?
Yeah.
So your question is, what is the average of n? And we can always write it. We can always write an average of any observable, and an integral from minus, when we are in one dimension, minus infinity to infinity, dx, side dagger of x, observable, side of x.
Yeah, I know. I mean, like physically, not calculations. I mean, you get the most common energy level.
If you have a single eigenstate, single mode, some n, let's say some general n but specific, what you're gonna get from kind n operator is just a number. So I can explain in 5 minutes more deeply to give you some examples, because it's gonna be. So let's remember this question. First, I want to introduce the bracket notation. Then it's going to be a lot easier for me to answer your question. What does it mean physically? The short answer is the number of the states. But let's give it 2 more minutes.
That's the expectation value?
We're going to get to it. Wait 2 more minutes. 5 more minutes, if you can ask. Okay. So, bracket notations. We have this phi n of x, right? But we are lazy. We are physicists. We don't like to write a lot of stuff. So, what we can write instead of phi n of x, we can define it as the mod number n with the cat. We can also write phi n of x conjugate as bra. So bra cat, this is bra, and this is cat. Bra and cat. This is just a method of writing stuff, which is very efficient. It helps us to describe system in an easier way. Listen. So, for example, if you want to know what is the expectation value of n, what we can write it as expectation value of n operator, we can write it as an integral from minus infinity to infinity psi, and let's say we have just a single mode, phi n of x conjugate n operator, phi n of x dx. Okay, we can instead write it as sum mod n operator. You can write it like this instead. We know that when we operate an operator on some specific mode phi n of x, this is equal to writing n operator applied on specific mode n. This is equal to n times n. Here it's an operator, here it's a value.
So it's n up to normalization.
So I can write it as n. This is a bit confusing. Here it's a state in bra, here is a state in cat, here is a scalar. So I can write it as, I can take this outside, and I have the scalar n times bra n, cat n, which form orthonormality, for normalization, this is equal to n times 1. Something which is nice to note is usually what we have psi of x, which is a sum over n from, I don't know, 0 to infinity, some coefficient or weight Cn times the mod phi n of x. And when we apply the n operator, when we want to find what is the n operator, we can apply it over this psi of x and get the, okay, so we can say, let's do it, n operator applied on psi of x is equal to, writing the sum over n equals 0 to infinity, Cn, because I can take it inside after all the scalars but not after the function. And then we're gonna get n phi n of x. What we have here is basically n times phi n of x. But if what we're gonna do, let's say what we're gonna do, we want to have the average value, so we can have, so let's take it step by step. So this is equal to n equals 0 to infinity Cn times n times phi n of x. This is just n applied to psi of x. So if what we're gonna have instead is some psi and psi, we're gonna have, this is maybe a good example, it's not in the notes, but we're gonna have, let's say, some index n1 from 0 to infinity, another index n2 from 0 to infinity. We're gonna have from the left side, we're gonna have Cn1 conjugate phi n1 conjugate of x, and from the right sum, and from the n operator, here it's n operator, we're gonna have this expression. So we're gonna have Cn2 times n scalar times phi n2 x.
N is also in 2, right?
Yes, correct. Now, from orthogonality, we can say that phi n1 and phi n2 is just going to be the phi n squared for some specific n, because if n1 is not equal to n2, we're going to get 0. So we're going to get some function of some n, it doesn't matter if it's n1 or n2, Cn conjugate Cn times n. This is equal to sum over all n, Cn absolute value squared times n. And this is exactly the probability to be at the state n. So when you have a sum, so we can say that any observable, any average value of observable, this is classically meaning, is like a sum over the probability to have this observable times the value of this observable. This is from basic statistics course. So what I did here is basically said, okay, let's say we have some function which is complicated, a sum of many different modes. I can just, and I want to see what is the average value of n operator. We get, it's the actual average state of the system. It's the average number of states. So this is the physical method for a question. Why I needed another 2 minutes before I told you all this? The reason is I could went to integration and solve it using integrations and all the tricks and stuff, but it would be, actually here it would be even the same, it would be it's going to have the same amount of difficulty solving it in integration, because all we had to do is write here some sum, then integrate over all x, and we get some average value. It's going to be almost the same. But I wanted to use bracket notations to make you more used to this concept. Okay. Questions before I erase it?
Do you save the last line?
Yes, I can wait another minute.
You can erase that.
Example. I want to compute some operator which is a dagger minus a dagger a on some state n and see what we get. So before it, I'm going to do a short recap of what you learned in the lecture. When we have an operator, two operators A and B, we have a commutation relation, which is equal to AB minus BA, minus or plus?
Minus.
Perfect. We can also have an anti-commutate relation, A comma B, which is equal to AB plus BA. Here what we have is basically a dagger over some eigen function n, eigenmod. Okay. So let's solve it. We can solve it using these relations and get that a dagger over n is equal to a dagger is square root of n plus 1 n plus 1. This is equal to n plus 1 n. This is on one side. On the other side, a dagger a on some state n is equal to a square root of n minus 1. This is a dagger, which is equal to n times an eigenstate. Overall, we got that a dagger minus a dagger a over some state n is equal to n plus 1 minus n on this state, which is equal to 1 times the state. So basically it does nothing. Which also gives us the result that the commutation relation between a and a dagger, which is equal to a dagger minus a dagger a, is equal to 1. This is very useful because you can use this relation, and anytime you have a dagger and you want to change it to a dagger a, you can just say it is equal to 1 minus 1 plus a dagger a. And this relation could be very useful for calculations.
That's the one for fermions or for bosons? I know Richard said something about it during the lecture. He said that they change, they differ based on the plus and minus there.
Yeah, because here you have a minus and you have here a delta, zeta, whatever, which is either, I think, it's plus for bosons and minus to fermions.
Oh.
But I'm not sure if it's a plus or minus, which one is which.
Yeah, I'm not.
But basically what you're gonna have, you're gonna have here some factor. This is a factor which is dependent on either it is bosons or fermions, and it's gonna be either plus or minus 1. I think it's plus 1 for fermions, minus 1 for bosons, and also you can see that if you write an A, comma B, and then you add this zeta, then for if zeta is plus 1, you're gonna get the commutate relation, and if you're gonna have minus 1, it's gonna get the anti-commutate relation, because this is basically equal to AB minus zeta of VA. This is some anecdote that usually we don't say in quantum mechanics 1, because you don't know what are fermions and bosons.
Yeah,
I don't know what are fermions and bosons. No, I know a little bit.
something about the spin, right? They can share the same quantum state.
I think the first point you really start to understand what are fermions and bosons are in statistical mechanics.
Not in quantum or quantum 2?
Maybe a little bit in quantum 2. They say we have Pauli exclusion, but you say, who cares? Like, it is important, but you don't understand why it's important. Maybe in the end of quantum 2. Okay, let's do a long and important example. We want to find the average value of x of t and the second moment for the harmonic oscillator case. Harmonic potential, meaning we have all the raising and lowering operators. This is why it's important to say harmonic oscillator case. We have those operators, and we can rewrite them as a n is equal to square root of n minus 1, and a dagger n is equal to square root of n plus 1 and plus 1. So this is what we're seeking, to know at some time t what is the average value of x and what's the second moment. And we know that the initial conditions psi of x comma 0, meaning at time t equals 0, we can write it also as psi 0 of x, is equal to 1 over square root of 3, phi 1 plus phi 2 plus phi 3 of x. So it's also important to note the factor of time. Okay, how we started? First of all, we can write that psi 0 of x, we can write our state as 1 over square root of 3, and then we can write 1 plus 2 plus 3. Look how much less I had to write. It's so much easier. Perfect. Now we want to find psi of x comma t. How am I going to do it? So for the harmonic oscillator case, we have a potential which is independent of time. So when we solved psi x of t, this is a short reminder. We had a
Multiply. Yeah, separation of variables.
separation of variables. We said we have some function of x times some function of t. Perfect. This function of t was e to the minus en over en over h bar t. So we start by, so we can solve separately the space solution and the time solution. Starting by this, we can just write e to the minus e1 over ie1 over h bar t plus, this is state 1, plus e to the minus ie2 over h bar t 2 plus e to the minus ie3 over h bar t 3. Perfect. Okay. We can write it explicitly because we know that the energies are equal to h bar omega and plus half. So I can write it explicitly and take outside and the f from everything. Meaning I can write it as e exponential of minus I omega over 2t was square root of 3 times e to the minus I omega t 1 plus e to the minus I2 omega t 2 plus e to the minus I3 omega t 3, and that's it. So now I'll remind a little anecdote about global phase. Usually when we have a global phase we can throw it away because we don't care about global phase. We can always choose one global phase. Can we throw away this term here?
No.
Why not?
Because it depends on time. And then it can change, right?
Yeah, but I can say it's 0. Because here we also have a dependence on time. I can say this is a global phase, we don't care about it. So a lot of the times, yes, you can just throw it away. Because when you measure, when you're gonna measure it, this time is not gonna have any impact. Because only the difference between those two terms, we have people here. Only the difference between those two terms are gonna be of importance. I can also take another e to the minus omega t outside. However, in this example, I set the initial conditions in time also. So I said at time 0, we don't have any phase. So it is somewhat important, but not a lot. Like, if you would forget it, I'm not sure it would be of high importance.
But how does the fact that you have an initial condition for time means that?
It is important because the global phase is like when we start. The global phase
but if you put 0, then you can still get 1, so you can just replace it by 1 and you wouldn't notice it.
Yes, that's what I'm saying.
So it's not that important.
It's not very important. We do keep it. We don't just throw it away because we want to show we know what we're doing. But it's very similar to what we had as a global phase. It's not gonna impact almost anything. Anyways, okay, we have psi of x comma t. Our question is, what is the average value of x of t? So we can write it as psi x operator psi. One way to do it is to integrate. To do a lot of integration, work hard. Instead, I'm gonna scratch my head and I'm gonna say, what can I do, what can I do? What I can do is write x as terms of lowering and raising operators. I can always write x operator is equal to h bar over 2m omega square root a dagger plus a, and p operator is equal to I square root of n omega h bar over 2 a dagger minus a. You can see it simply by saying, okay, if we add up these two equations, so this plus and minus disappear, this is subtract, those two x disappear. So we can evaluate x and p as a function of a and a dagger.
Can any operator be written as a superposition of
Other operators?
of these two specifically?
For this we need the a and a dagger operators behave as a complete set of all the operators, which I'm not sure they have. So I think the short answer is going to be probably not. Maybe in this specific case, because the Hamiltonian depends only on p and x, so all we care about is, so if we know what is the Hamiltonian at any time, we know everything. Because the Hamiltonian is like a full description of a system. So maybe this case, but just because we don't have anything other than x operator and p operator, and also remember this lowering and raising operator are specific to the harmonic oscillator system. It's not something which is global. It's not like any state is gonna increase it or lower it. We showed it for harmonic oscillators, it works for harmonic oscillators. Anyways, we want to solve this monster, which is equal to square root of h bar over 2m omega psi a dagger plus a psi. When I write it psi, I mean psi of x and t. Some general x, some general t, which is exactly the expression we have over here. Okay, let's write it. H bar over 2m omega. With 0, with 1, 2, and 3. So 0 can go to hell, so does 4. And what we get is square root of 2 a to the minus I omega t. Let's do it simpler, because those are constants. So let's start with the term of 2. Say this is a to the minus I omega t square root of 2. And here we have plus a to the minus I 3 omega t square root of 3. Plus 1 a to the minus I 2 omega t square root of 2 plus, let's have this in parentheses, plus 3 a to the minus I 2 omega t square root of 3. Nice. This is horrible. This is very, very horrible. And we're gonna do it all over your homework. A lot of times. What is x of t? So we can say it's h bar over 6m omega. Let's combine terms. So let's do it. Let's start with the 1 first. So we have 1. We know that 2 doesn't care for it and 3 doesn't care for it. 1 is gonna say 1 and 1, var 1, ket 1 is equal to 1. While var 2, ket 1 is equal to 0 and so on.
Square root of 2 e to the minus I omega t.
So we're gonna have square root of 2 e to the minus I omega t. Nice, good, perfect.
Yeah.
Plus, let's do the term of 2. Just because it said 3. So we're gonna have a to the I 2 omega t, a to the minus I omega t square root of 2 plus a to the minus I 3 omega t square root of 3 plus the term of 3 is gonna be e to the I omega t square root of 3. Perfect, this is so much fun. Equal to h bar over 6 omega square root of 2 e to the minus I omega t plus square root of 2 e to the minus I omega t plus square root of 3 e to the minus I omega t plus square root of 3 e to the I omega t. This is equal to
cosine, right?
Right. H bar over 6 omega 2 square root of 2 e to the minus I omega t plus 2 square root of 3, and we can take this 2 and this 2 and write here 3. The cosine omega t. So easy. Does it make sense?
No, something doesn't have that.
Why doesn't it make sense?
Because you don't have the same factors for plus and
Because I have something which is imaginary. So I made a mistake.
yeah.
Why is it here
You get
minus?
a
It's a
plus.
plus.
Yeah.
So now we have square root of 2 plus.
So you can take the square root of 2 plus square root of 3 outside.
Let's do it. Square root of 2 plus square root of 3 cosine omega t. Okay, it's very important to see what we have if it makes sense, because if I'm gonna read the test and it's gonna be like, okay, the average value of x is some complex number, I'm gonna be, this is shit, and you should have known it. I'm gonna put like a large x, red x, and I'm gonna be like, this is wrong. So when you have a solution, you see, okay, what do we have here? We have some oscillatory behavior. This is great, we have an harmonic oscillator, we are happy. Like, if you're gonna fuck up the constants a little bit like I did, like I forgot here, there's supposed to be some 2 here, I don't know. I don't care, I wouldn't care even. Because if you get the units correct, and you get the general behavior correct, I would be happy. But I'm not gonna check your test, so. So why would you care? Okay. Do we want to do something harder? Yes, please. Let's. Hold up. Okay, so let's rewrite psi of x and t. This is e to the minus I omega over 2t or square root of 3 e to the minus I omega t1 plus e to the minus I 2 omega t2 plus e to the minus I 3 omega t3. I'm writing small because we're going to do the second moment. So the second moment we have what? Okay. I'm not gonna solve it explicitly. Just the start part of solving the second moment x squared of t, and the rest is gonna be for your homework probably. How do I do x squared of t? What we're gonna have is gonna be graph psi x operator squared cat. What is x operator squared? So we're gonna have here h bar over 2m omega psi a dagger plus a dagger plus a psi. This can be written as a dagger squared plus a dagger a plus a dagger plus a squared, all with the little hats, of course. We love small hats. But at some point we will forget them. Nice. So, this is a little bit complicated. How do we do it? How can we solve it? One way to simplify this expression is use the coventation relation that a dagger a, which is equal to a dagger a plus minus a dagger. And I think maybe it's a dagger, not a dagger a. Let's look.
Hold up. And that's okay, right? Using the definition.
A dagger. Yes. This is minus or plus? This is minus. This is equal to 1. Therefore, we can say this is equal to. Let's write this a dagger a plus 1 plus a dagger a. Right? Because we took this a dagger and replace it with 1 plus a dagger a. So, what we have for x, not even close, x squared is equal to h bar over 2m omega psi a dagger squared plus a squared plus 2 a dagger a plus 1 psi. Okay. Here we have 3 terms for the psi, 1, 2, and 3. And we have 1, 2, 3, 4 terms to calculate. This is very hard. This is very complicated. But before when I said, okay, I'm gonna just do some way, but there is an easier way. The easier way, or more careful, maybe a bit longer, but easier way to do it, is gonna say that this is equal to h bar over 2m omega psi a dagger squared psi plus psi a squared psi plus 2 psi a dagger a psi. A dagger a is familiar for somewhere.
N.
N psi plus, and we have psi 1. Now, first of all, it looks a lot less fearsome and cool from the first thing we had. Now, what we're gonna do, we're just gonna solve first the expectation value of a dagger squared. This is gonna be our first step. The second step is gonna be solving the expectation value of a squared, and so on. Questions? Great. This is why for homework it's gonna take like 10 hours, and the lecture is only like an hour and a half.
Are there a lot of questions in the homework?
Oh, plenty. It's because last week was an easy exercise. Okay, questions before I erase this side. Oh,
Press it.
I'm safe. New subject. Coherent states. Coherent states are defined specifically for the lowering and raising operators of the quantum harmonic oscillator. So we are like okay, let's do some oscillator. Let's go deeper. Quantum harmonic oscillator. Let's go deeper. Raising and lowering operators, which are dedicated for these harmonic oscillators. What is coherent states? Coherent states are the eigenvalue, the eigenstates of the lowering operators. Meaning, coherent states, we denote them as alpha, usually, and we say that the A operator applied on alpha will give us alpha times alpha. A few points to note. The first one is those states, those coherent states, are an eigenstate of this operator, which is not an Hermitian operator.
So we can
So those alpha doesn't have to be real. They could be complex. If you want to see what happens when we apply a dagger on alpha, it's not going to be equal necessarily. It depends on alpha. It doesn't have to be equal to alpha times alpha or whatever. Or some. It doesn't have to be some eigenstate times alpha. What is it? We can just take the dagger, the conjugate of both sides. And what we're going to get alpha A dagger is equal to alpha conjugate. Meaning, while the lowering operator is defined on the cat, the raising operator is defined on the bra. This is a little bit confusing because a lot of the times, because what we did in the start of the lecture is we applied both A on some eigenstate n, and then we applied A dagger on some, let's say, other eigenstate n. Now I say you cannot just apply it like this. So you need to apply on the coherent state, you apply A on the cat states and A dagger on the bra states. Questions? Right, let's do an example. Let's assume we have some particle in a coherent state alpha naught. Let's do a little bit of blue. Blue is for the weekend. We want to find the expectation value of x in this, with regards to this coherent state. Meaning, we want to calculate what is alpha naught x operator alpha naught. Interesting. So we write x as, we use the x operator, the relation to the raising and lowering operators. H bar over 2m omega times alpha naught a dagger plus a alpha naught. Now we're going to do something a little bit careful regarding what I told you a minute ago. We are going to apply a dagger on the bra and a on the cat. I can't do it any other way. So this is equal to h bar over 2m omega square root. Alpha naught, I apply first a dagger on alpha naught, so I'm gonna get, okay, let's write it in, let's have another step. We can write it h bar over 2m omega, because this is what I'm doing when I have some unclear operators. So alpha naught a dagger alpha naught plus alpha naught a alpha naught. Okay, I'll just write it in two terms. So for the first time with the a dagger, I'm gonna get alpha naught. Let's edit that. Alpha naught. When I write a dagger, I get alpha conjugate. Then alpha naught plus alpha naught. Alpha is from the lowering operator. Alpha naught. Those are now scalars, the alpha and alpha naught. So we have square root of h bar over 2m omega alpha conjugate plus alpha naught. If alpha, because alpha is some alpha naught, and this is also alpha naught. Because alpha naught is some complex number, I can write it as, and let's write, I don't know, let's write it capital A plus I capital B, when A and B are real numbers. Alpha naught conjugate plus alpha naught is going to be equal to 2A. This is equal to 2h bar over omega. Real part of alpha.
2 alpha naught.
I put the 2 in the square root.
Oh. Oh.
Furthermore, this is equal to 2 square root of 2 sigma x real of alpha naught. In the same manners, we can calculate the average, the expectation value of the P operator of this coherent state, and we're gonna get square root of 2 sigma P imaginary part of alpha naught. Let's just write it here, the two terms we got, square root of 2 sigma x real part of alpha naught. Very interesting. This means that we can write alpha naught as 1 over square root of 2 sigma x over expected value of x plus I over square root of 2 sigma p expected value of t. That is, a coherent state is something which holds both information on both the position and the momentum. when it's something which is very close to have, it's something which has some classical meaning. So first of all, so what do I mean by some classical meaning? We have something, we have some object which gives us information both on space and momentum, but on average, on the average limit. This is basically almost like the classical limit of some state. This is why we call those coherent states a quasi-classical states, because they are like similar to some classical states.
Alpha naught is a general.
General coherent state.
Oh, okay.
So we can have alpha naught could be basically almost anything, as much as it applies that if you apply a lowering operator on alpha naught, you're going to get alpha naught times the same state. So it should be some eigenstate of this operator, not of the Hamiltonian, of the lowering operator. Therefore, you're going to get and this is very interesting because I don't fully understand it. What we have here, we have something which is not Hermitian, some operator which is not Hermitian on one hand. On the other hand, its eigenstates give us something which is like almost classical. It has some classical meanings. Questions? Okay, bye.
You finished?
Yeah. Have a nice weekend.
See you too. יש הרבה עבודה לעשות. זה באמת כזה ארוך?
כן. The homework is long, it's horrific, horrible. You're gonna have so much pain, you're gonna feel so sad when you do it because it feels like such a big pile of bullshit. But then you're gonna go on to quantum mechanics 2 and you're gonna be like, okay, we have it all over again but now harder. And then you're gonna go to advanced quantum mechanics like me, and I'm doing this, and I'm doing right now homework regarding those creation, annihilation, or raising and lowering operators, and I'm suffering so much. So enjoy the moment. It's not gonna end. It's never gonna end.